Hello, my name is Erik Fender,
And my name is Brady Cordaro.
and our presentation is on STATCOMs. We'll be modeling STATCOMs from a controls perspective and analyzing why they're so important to the power grid in today's modern world of technology.
So to start out with, we're going to talk about what is a STATCOM. As a reminder, STATCOMs are power electronic devices used to control reactive power through a network by either acting as a sink or a source to increase stability of the power grid. STATCOMs look to take the place of the much larger in size and less versatile SVCs. Our goal was to successfully model a STATCOM using various techniques and technology. And challenges we faced was when choosing the project, we intentionally took on a more complex control system that interested us. Due to this though, we had found the project being a little challenging to model due to the complexities within a STATCOM. It is not a simple control system, so finding this transfer function and simulating ended up being a more daunting task than we thought originally. So, black box modeling. Black box modeling is a technique that allows the use of inputs and outputs to model systems without the knowledge of the actual inside working or internal working systems. How this relates to our project is because it is such a complex system, it is easy to get lost. So if you go ahead and just take the black box and cover up all the internals, you can just see the VDC as an input and CVW as an output, which we couldn't really work going forward. So as we move further into our project, we're looking to use actual variables to put into the black box and receive output. So the STATCOM works as a basic principle. You have the reactive power flow equation, and the goal of the whole entire thing is to maintain a delta to be 0, and the delta is the angle between V1 and V2. So the equation of the reactive power flow is right there. And in short, there are two possibilities for reactive power flow, where if V1 is bigger than V2, the Q will flow from V1 to V2. And if V1 is less than V2, the Q will flow from V2 to V1.
So, the STATCOM works by either absorbing reactive power or supplying reactive power. And that depends on which way the current is flowing across the X on the top right. And what determines the current there is your reference voltage, really the internal voltage of the electronics. It's a DC voltage, which is labeled there as VSC. Now, this voltage is determined by measuring different aspects of your grid, like voltage, current, and other various aspects of it. Now, this is a model of a STATCOM within a whole entire grid system. So we have the STATCOM over here connected as a shunt with the whole entire grid. This is a 60 Hertz, 500 kV grid like you'd find very commonly in the United States. So that's just showing how it would be implemented. Now this is the whole entire detailed model of a STATCOM. In the top left we have the actual STATCOM itself with the power electronics. In the top right we have a phase lock loop, which is inside the STATCOM, but it's really hard to show in a model like this. Next we have the closed loop controller, which we'll circle back to in a minute because that's the key of this whole entire model, with a reactive component estimation, which helps with the measurements for our electronics. Our pulse width modulation works in conjunction with all of these here to control the electronics for controlling the grid. Now, over here are results. We'll get to that in a minute. And the most important thing here is this is a voltage regulating STATCOM. There are two kinds, the other kind being a power regulating STATCOM. Both regulate power, but this one functions off of voltage, the other one functions off of power. Now, so here's the single phase STATCOM. Basically, this is controlled by having a shunt capacitor. This just models the internal resistance and is measured, and from this measurement and the measurement of the grid is how you compute those to get your pulse width modulation, which control each of the electronics of the grid, rather of the STATCOM. Now you've got your phase lock loop. What this basically does is extracts the real and not the complex, but the imaginary parts of the power or voltage in your grid. And we got the reactive component estimation. That's just a further computation help with computing your electronic aspects. Pulse width modulation. This is, again, this is what actually directly controls the electronics, but this VREF comes from our controller, our closed loop controller. Now this is quite complex, it's really hard to analyze, and so there are actually simplifications of this grid available that you can research and find. Now, you can simplify this into this very simple block diagram with the, not a transfer function, but rather an output function labeled here. And if you assume that VREF is 0 because we're trying to go to steady state conditions here, but because of what we're trying to measure, VREF is 0, and we can find the transfer function here, and G1 is this, G2 is this, and you can just dive into that and make it all nice and messy, and it's a long thing, but we can have it simply right here. Also, a quick note, under steady state conditions where S goes to 0, we have this transfer function here. Now the results from this part of the whole entire model are shown as this. This is where this particular model also reflects the larger model, 60 Hertz, but we had the voltage lower so we could have a little bit better detail of what's going on. So at 60 Hertz, we notice that V grid and I load are very stable. V grid because you have a generation plant supplying a steady load, steady voltage. And what's going on now is you have transients, as you have transients in the larger grid from I grid and I inverse, what the STATCOM does is it supplies a steady current and therefore steady power to your load, which is very important. The customer needs a steady load, right? Now here's the VDC scope. What this does is this shows the internal DC voltage of the STATCOM as it rises from 0 all the way to your steady state of 400. And what this means is that this is showing how the STATCOM internally is reacting to these transients.
Yeah, so moving forward, the next steps would be to take any feedback you're given and fix any issues or missed topics as part of going back and using the black box, because we want to access that a little more. We're going to research the controls aspects of the STATCOM and explore using bode plots, pole zero graphs, root locus plots, impulse and step response, and look into time responses and identify any over or undershooting that may be occurring. And we would like to finalize this project by the last week of April to ensure we meet the May deadline of May 1st. And these are our references.
Thank you very much.